get this going. There we go. And once again, for everybody here, we're going to do our presentation here from 7 to 8 or whatever it takes. Before or after that, then we'll have a little break, and those who want to leave can leave. The rest of us will go on to our monthly meeting with that. So I'm going to start out with a little introduction that I have about our speaker tonight, Katherine Melbourne. Now, I took this off the internet, so correct whatever's out of date or wrong here, but I'm going to read a little bit. Okay, you are a policy analyst in the Center for Space Policy and Strategy at the Aerospace Corporation. In this role, she writes about national security space strategy issues informed by technical understanding and supports the development of tabletop exercises to test proposed policies and processes. Prior to joining aerospace, she was a systems engineer at Ball Aerospace, now BAE Systems. There, she worked on a national security program and served on the commissioning team as a wavefront sensing scientist for the James Webb Space Telescope, helping to align its mirrors. She designed a war game for the United States Space Force on cislunar operations and strategy during her time as graduate research assistant at the University of Colorado Boulder. She has previously published work on stellar activity and its effect on exoplanet habitability and assisted with drafting and negotiating agreements between NASA and its foreign partners. She earned a bachelor's degree in astrophysics from Yale University and a master's degree in aerospace engineering from the University of Colorado Boulder. So now I will introduce officially Katherine Melbourne on the title of her talk tonight, which is Orbital Mechanics and Political Dynamics, the Physics and Strategy Behind Space Warfare.
Awesome. Welcome. Thank you. I appreciate it, Randy. I'm going to go ahead and share my screen, and then you got to tell me if I am doing it right here. So, you see it okay?
Yep. Yeah. This is the PowerPoint. Good.
All right. Sounds good. Well, yeah, I think that introduction covered a lot of what I was going to talk about in the first slide, so that's good. But I want to point out that I'm in a way, a NACRL member. I joined the Popular Astronomy Club back in 2013 in Davenport, Iowa. So this is actually like 18-year-old me here with my astronomy club. And going to the National Astronomical League convention in 2016 actually helped me kickstart my career in space policy, because I met Charlie Bolden, who was then the NASA administrator at that, and spoke with him about, maybe working at a NASA center someday. And there was an internship opportunity in the International Relations Office. So I got connected with him and ended up taking a semester off to work there. And so that's what the drafting agreements is. But as you can tell from my background, I'm kind of a jack of all trades, master of none. I really, really fell in love with astronomy and then moved my way into like space sustainability and through that space security. But I'd say like highlights of my career so far are definitely working on exoplanets, working on James Webb, and now space policy. So I do also, in addition to like the technical side of space policy, I do a lot of comparative work. So I'll do a lot of the international work. And my most recent paper was on Taiwan and their space industry, which is not to be overlooked, surprisingly. So we'll start with doing a little bit more. I don't know if you guys can see. All right, there we go.
You want to start the slideshow, Katie? We're seeing the PowerPoint, but not the slideshow.
Oh, weird. I thought I was starting that. Hang on. Let me go ahead and stop sharing and then reshare my whole screen.
Okay.
And then it will do that. All right. From current slide.
Okay.
How's this?
There it is. That's the point.
Is that right? Okay. Yeah, I think I just selected the PowerPoint. So there we go. Okay. So space is a warfighting domain. I'll set the scene here. I think before we got to get into the physics, as a policy analyst, I have to talk a little bit about the strategy. So this obviously makes everyone's heart race a little bit when you hear these words, but I'll set why this has been kind of the rhetoric recently. So space has been very important for national security since the 1950s. And we've had reconnaissance satellite programs that literally sent up film imaging capabilities and sent that film back from space. A very famous example of that is Corona for original like spy satellites. So traditionally, since then, space has been viewed as a support domain for other military functions. But especially since the advent of the Space Force in 2019, more and more of the rhetoric has been focused on space as a supported warfighting domain. So, in and of itself, a place where we could fight a war, even though that makes us all very anxious. This description was used in the Department of Defense's last space strategy or defense space strategy update in 2020. And recently, in earlier this year, they came out with a space warfighting framework. So that's where they first leaned into the idea that you can do offensive space attacks publicly for the first time. So the point at which a domain becomes a warfighting domain is really fuzzy. But being a warfighting domain doesn't necessarily you're also having an active conflict there. So for space, some considerations as to why it could be considered a warfighting domain is it's used for projecting power around the world. It can be contested, so an adversary could attack one of your assets in space, and that includes from other domains to space and from space to space. And activities in the domain affect people's lives and their livelihood, their money, their quality of life. So that makes it a national security interest. And at this point, counter space weapons are being used on the regular in a range of their effects and capabilities. And these are all discussed and included in the warfighting framework. So we'll get into a little bit of what those are. But first, I feel like something that's really confusing is what is some of the differences between all these different space organizations. This chart you don't need to know in super detail, but the main thing I want to emphasize here is kind of the difference between Space Command and Space Force. So part of the drive behind all this rhetoric is that culturally, the Space Force wants to establish that their guardians, which are members of the U.S. Space Force, are just as much warfighters as any other military members of any other branch. And so that's why you'll hear space as a warfighting domain. Another part is the desire to prepare space operators who are working in that field to start making decisions on the timescale of a warfighter, quote unquote. So on the scale of seconds to minutes instead of weeks to months. So tactical level decision making. Operations in space are also guided by joint doctrine as well as these USSF Space Force specific doctrine, which are issued by the Space Training and Readiness Command, which is over here on the right and one of our field commands. So the Space Force is in charge of organizing, training, and equipping the branch, which is then taken on, all of those resources are taken on by these three field commands here on the right. And then the component field commands to the left of that on the chart, kind of in the middle, integrate the Space Force with other military branches and support their specific combatant commands, which are, we only have one listed here, which is the United States Space Command. So each of the different organizations here support a specific mission, support a facility support function, or support space launch. Now, Space Command is one of the combatant commands, as I just mentioned. And so that's the group that uses all of the resources that's provided by the Space Force. And its organization includes both service components and functional components, which are down here. The slide is very high level, and there's a lot of reorganization happening. An example of this is, I'm sure you've heard about like the change of name to Department of War. That's still ongoing. And another example is that the Space Operations Command, SPOC, which is here in the middle, is actually, as of this week, renamed to the Combat Forces Command. So it's kind of aligned with this whole idea of increasing offensive capabilities in space. So now I will get into a little bit more about the space warfighting framework before we get into the physics. We're almost there, I promise. But the space warfighting framework defines space superiority. And that's really important because that is a U.S. goal in space. So space superiority is defined by them as, quote, a degree of control that allows forces to operate at a time and place of their choosing without prohibitive interference from space or counter space threats, while also denying the same to an adversary. So it defines superiority here on the left as both a spatial and a temporal dimension, and recognizes that it's unlikely that you're going to have superiority in space all the time in every location. So the achievable goal that they're looking for is all the time, at least in a local area, and depending on what is most strategic in the and necessary in the time being. And then the framework also outlined possible space futures. So here on the right, you'll see kind of what they think on the y-axis, the blue space capability, quote unquote, which is like the United States and allies, versus the adversary capability. And something that's super notable from this chart is that they note that an outcome where both the U.S. and adversary capabilities in space are denied is bad for the U.S. And so this is really important because it emphasizes this long-held belief that the U.S. has an asymmetric reliance on space that puts them at a disadvantage compared to adversaries who don't necessarily need space as much to fight the fights that they want to fight on the ground. So this is really interesting, and it reaffirms some of those assumptions. But I highly recommend reading more into it if you would like to. So now talking a little bit about counter space weapons, but before I do that, I just want to make sure, are there any questions yet?
Yes, we have one.
Okay, yes.
In the first part of your talk, does the battle over where the Space Command headquarters, Colorado versus Huntsville, Alabama, how is that going to affect anything?
That's a good question. So right now, I think it might affect who ends up wanting to work in Space Command. I'm not sure that that's like an absolute thing, but I personally know a few people who have actually moved from Space Command and come over to their company. I don't know if that's related, but that's an interesting just kind of anecdote. But I think it's much higher political issues that cause that, right? So it's comes down to Congress people who are fighting for their districts and saying we really want this here. So I don't foresee it necessarily affecting our capabilities on a whole. It might just affect individual people and their decisions. So I don't know if that's helpful, but yeah.
Yeah.
All right. Okay, so I'll get into some of the counter space here. This is kind of a scale here where you'll see reversible to non-reversible attacks and then space situational awareness on the far left, and I'll get into this. So with the space warfighting framework, space superiority is enabled by space control, which comes from implementation of effective counter space operations. So this is where an attacking force will intend to deceive, disrupt, deny, or degrade, or destroy an adversary's capabilities so that they can take advantage of the access to space that their adversary no longer has. So when assessing a counter space capability, there's some really key considerations. First off, is there contact between the two objects at play? So the interceptor and a spacecraft. So if so, that's often referred to as a kinetic attack, which is somewhat of a misnomer, but it's commonly used. So we'll use kinetic to refer to any physical engagement or contact between a weapon and a target. Non-kinetic is the opposite. So when an attack doesn't physically touch the target. Another consideration is the attack reversible or non-reversible, as the scale shows here. So both kinetic and non-kinetic attacks can be reversible and non-reversible. It's much less likely that a kinetic attack is reversible, though, since you're physically engaging with the object. So this reversibility is based on whether or not the object's capability is permanently destroyed by the attack or only temporarily damaged. And then the last kind of thing that you need to think about is there physical damage or are you damaging their signaling capabilities? So you can do physical damage to an object in space without a kinetic attack. So you can use a directed energy weapon like a laser. But you can permanently damage electronics from that. Or you could just jam their signal, for example. So that's the third dimension. So we assess if an attack is kinetic, reversible, or physically damaging to a spacecraft. And we also look at attribution, which is where these three things in the side, the left here, come into play. So supporting the use and attribution of counter space capabilities is figuring out space situational awareness. So that's how we observe, track, identify active and inactive space objects. And then space domain awareness is something you might have heard of as well. It's a broader term that includes space weather analysis, as well as studying the intent of actors. And we'll get into that a little bit more later. But there's also this idea, I know there's a lot of information for this slide, of space capability being dual use. So a lot of times space capabilities will be developed for civil or commercial purposes that could also be used in a security context. Starlink is a really good example of that. It's a commercial product that is very key to our national security. So is grappling a satellite for active debris removal that could be used nefariously against an active adversary satellite. So in many cases, when you have these dual use capabilities, you just need to consider what is the rhetoric surrounding them. And I'll get into one of the examples of this a little bit later, but that's just something to keep in mind when you're hearing about a particular space capability. Okay, so cooperation to conflict continuum. I think this is my last strategy slide before we get into the physics. So thank you for bearing with me. So when comparing how two states are engaging with each other, there's a continuum from cooperation to competition to armed conflict. And so it's really debatable who you ask, but where we are in the competition to crisis phase right now, I'd put us about there, where we are definitely in a competition mode, but we're not actively fighting a war in space. So that's where I would put us. Now, counter space capabilities are being used in space today, as I mentioned. So this is a chart from, and forgive me for the bad resolution on this actually, but this is a chart from the Secure World Foundation's 2025 Counter Space Report, where they report on different countries' counter space capabilities. So green is no capability, yellow is some, red is significant capability. So one of the things that is particularly notable is that direct ascent anti-satellite weapons have been tested by several countries, including the US, on their own satellites. So they've never actually been used in a conflict, but they have been tested. And recently there's been more news about rendezvous and proximity operations that have led to grappling and docking demonstrations that could be a display of force. Electronic warfare is used all the time for jamming. It was used before Ukraine, the Russian invasion of Ukraine, to jam Viasat satellites that were giving information to Ukraine. And I will also note that of all the things on this table, they do not include nuclear attacks, ground site attacks, or cyber attacks. So those are also important to consider, but aren't really the focus of this talk. And as I mentioned before, these can be categorized into the kinetic physical, non-kinetic physical, and non-kinetic non-physical attacks. Yeah. All right. So as you all know, I'm sure, the strategy is constrained by physics. So we need to understand how objects move through space and on orbit. And the different types of engagements, and also how directed energy and electronic warfare work at a high level in order to really understand what these capabilities are. And so when I give the rest of this talk, it'll be mostly on space-to-space and ground-to-space weapons, not on this other idea that you may have heard of, rods from God, quote unquote, which is space-to-ground weapons. They were discussed during the Cold War, but weren't put into practice. So this may be review for some of the more like science engineering focused people in the room, but bear with me because I do think that it's important for gaining some of the intuition. But before I go into some of the basics about orbits and maneuvering, is there any questions on the strategy?
Yeah, there's a question on the chat. Steve's asking, what can you say about Starshield?
Oh, that's a good question. I can't say too much other than there's a lot of talk about how do we use our commercial assets. in a security context. Like, how do we ensure that our contracts are such that we are protecting that asset versus and that we also maintain access to that asset. So that's all wrapped up in the Star Shield conversation.
Thanks.
All right. I will get into some of the orbital information here. So this is the fun part for me. As in college, or in grad school, my focus was on astrodynamics and satellite navigation. So this was more of what I did in grad school, and I haven't gotten into the math in a couple years. But I use it to inform, like I use this background to inform some of the policy recommendations that I write about. So starting with the fundamentals, satellite speed is determined by its orbit and altitude, not by its mass. So higher altitude means you're going with less speed. And in a circular orbit, you're maintaining the same speed around the entire orbit as it keeps the same altitude. But elliptical orbits, the altitude is changing, and so you're going to be moving faster when you're closest to the Earth at perigee and slowest when you're farthest away from the Earth at apogee, as you see in this first picture in the top right. There are 6 main orbital elements, and we're not going to go over all of those in detail, but the orbits themselves, they can be used to classify orbits themselves, and those are low Earth orbit, medium Earth orbit, geosynchronous or Earth orbit, and highly elliptical Earth orbit. So LEO, MEO, GEO, and HEO conveniently. And these are the different regimes that you can see them on in the second picture. HEO is particularly useful because it can reach higher latitude regions where geosynchronous satellites can't reach. So they also have longer dwell times over certain areas. So I think I have a slide where I show a demonstration of that. But first, I talk about one of the most important orbital elements, inclination. So one of the orbital elements is inclination. Satellites orbit on a plane that essentially extends through the center of the Earth. So that angle between the plane and the Earth's equator is called its inclination. So something to consider for security more broadly is that you're not necessarily fighting a war in the space domain, but you're trying to provide a certain amount of ground coverage with your satellites. So there's 2 extremes of inclination. There's a 90-degree inclination, which is the polar orbit. And through the polar orbit, because your Earth is spinning underneath you when you're in a polar orbit, you actually pass over every point on the Earth. And at 0 degrees, you only pass directly over the equator. Your satellite only goes over the equator. So essentially what you can extrapolate from that is that satellites only travel over points on the Earth with latitudes less than or equal to their inclination. So higher altitudes allow for an increased visibility across the Earth's surface as well. So if you're in GEO, you're going to see more of the Earth than you are when you're in LEO. And additionally, satellites also move with respect to the ground in all cases except for one very special orbit called geosynchronous orbit. And that's when satellites will appear fixed over a particular spot on the equator at 0-degree inclination. So establishing constant coverage over one spot on the Earth requires a constellation of satellites. So that's why we have Starlink and things like that for constant coverage. I think hopefully maybe I can play this video without playing the sound. So going over to back to the HEO orbits, I just think that these are super, super interesting to watch and kind of get this idea of ground tracks being very particular for different orbits. So HEO is the highly elliptical orbit, and there's 2 special types of HEO orbits, Molniya and tundra orbits. So the first one is this yellow one is Molniya, and so it's used for communicating with assets in higher latitude. So you can reverse it, and it'll be 60. Here, I'll play this again. It'll be at 63.4 degrees inclination, but you can also reverse it and do it at what is that, 126 degrees inclination, so that it's either over the northern hemisphere or the southern hemisphere. And tundra orbits are a different type where they're highly inclined and elliptical as well, but they have a 24-hour orbit period like GEO. And they're helpful alternatives to GEO because the satellites reach higher elevation angles in the sky so that at the higher altitude, at higher latitudes, you can still observe one part of the Earth without having to be over the equator. So that's when you see them and they're just kind of hanging out over one section of the Earth. But they're not at the GEO orbit. And so both of these types of orbits are at 63.4 degrees, like I mentioned, which is called a critically inclined orbit, because at that orbit, spacecraft don't have to deal with perturbations caused by the Earth's oblation, which is the fact that the Earth isn't entirely a sphere. So I know that's a lot of information, but the summary of the important parts are that ground tracks are important, and that's affected by inclination and altitude. And so another thing that you need to keep in mind is that satellites move very predictably. So unless a maneuver is performed, their orbit doesn't change. One exception of this is perturbations. So as I mentioned, the Earth isn't entirely a sphere, and so that changes the way a satellite moves in its orbit, as well as the fact that, sometimes when you picture, we're orbiting a mass, we're just orbiting the Earth. Well, there's also pull from the moon, pull from the sun that does come into play over time. Additionally, there's atmospheric drag. And so if you're really, really close into the atmosphere, you'll experience the drag when you go through it, as well as solar radiation pressure. There's actually designs for specific satellites that will take you far out in space with little fuel based on solar radiation pressure. So we won't get into these in a ton of detail, but these are just to keep in mind that they're part of the maneuver equation. So those were the start of the basics. Does anyone have any questions at this point? I have a few more slides, I think.
Yeah, you have a few questions, John.
Yeah.
Yeah, hi. I had a question about those orbits you're talking about there. So I take it that that some of them are pretty well inclined and very elliptical. And
Yes.
so it seems like the part where it's going to hang out the most is at apogee, right? That's
Yes.
also the place where it's going to be the farthest, but that's also going to be the place where you get the biggest view. So if there's a particular area of interest, would you put that under where the spacecraft is at apogee in order to get the most time over it and the biggest area of view? Or would you put that under where it is at perigee so that you would get the closest view?
That's a great question. Yeah, so it really depends on the purpose. But I know that a lot of those orbits are used for broadcasting. And so if your power is high enough that it can account for the distance away, like that you're further away when you're broadcasting over a broader area. But if you can account for the power and broadcast with more power, then you are still okay. So for the purpose that they're mostly used for, being further away is okay. Now these orbits can also be used for security purposes. You're not always necessarily looking directly at the Earth. You're also looking at other things in space. And so there could be a reason to use these orbits for that. And that's kind of similar to why some of the Lagrange point orbits in cislunar regime, which I don't actually get into that much in this talk, are used.
Exactly.
Do we have any satellites that move in a retro or counter orbit?
I believe there are satellites that do that. I can't think of any examples off the top of my head, but it's very it's not common because it's way easier to launch when you're launching with the rotation of the Earth. So I'm not sure like what the purpose of doing that would be. There are some instances when you would want to do that. Like I'll talk a little bit later about like tail on and head-on collisions in space, and so you might want to launch retrograde for that, but I don't know of a good reason to do it. So I'm actually going to look that up.
I was thinking defensively it would be an easier way to take out other satellites.
Yes, it is potentially a way for use in ASATs. Yeah, anti-satellite weapons. Yeah. Okay, were there other questions or?
Okay, that brings up another question to me then. Are there orbits that it would be much harder for an enemy to attack that spacecraft?
Yes, there. Well, around Earth, there are some reasons to potentially attack from one orbit versus another. Another thing that I don't talk about much, which I think would be a really good follow-on, is talking about cislunar orbits. So those are very variable, and I feel like every time that there's a new paper, they come up with a new cislunar orbit where satellites can find a point of stability and hang out and for a while until they need to make a maneuver for an attack or something like that, in theory, in the future. So that would be a very, very particular region where I would say that's it'd be challenging to attack, is in cislunar. But I'll get into some of the specifics of the Earth orbits soon.
What is cislunar?
Oh yeah, sorry. Thank you. Thank you for calling me on my jargon use. So cislunar is anything beyond geo. So you'll sometimes hear it as ex-geo or cislunar, and so that basically means any orbit in the Moon Earth system. And so it could be orbiting the moon, it could be orbiting a Lagrange point, which is a balancing point in gravity in the Earth Moon system, something like that. So it's further out, and it's a whole field of study in and of itself, because it's very particularly useful for space domain awareness to have certain satellites in cislunar orbits. Okay. All right. Stop me if there's anything else. Okay, so this is where I get really excited, because I hear about this a lot. Dogfighting in space. So maneuver is one of the classic principles of war, and it's long been thought of as part of strategy in other warfighting domains. So maneuver in the military sense means movement for effect. But in space, we use it to describe, obviously, like changing orbits, whether that be altitude changes or plane changes. So dogfighting, which normally applies to like aerial combat between two planes, it's been a term used in the news recently to describe interactions between space objects and maneuvers in space. And this invokes a certain Star Wars-esque image of spacecraft flying through space like airplanes. And so while this feels intuitive, it's actually the wrong way to think about maneuvers in space. Maneuvers expend fuel, first of all, which is a limited resource on a spacecraft. And there's also currently no infrastructure to refuel on orbit. Maneuvers also take significantly longer than you might imagine, which we'll get into. But the military utility of increasing maneuverability on orbit has been debated. And it involves answering questions about the technical feasibility, the strategy and why you'd want to do it, and other capabilities the system would require, like the refueling logistics. And it also means defining what a position of advantage even looks like in space, because that's another warfighting term, is finding a position of advantage through maneuver. But what does that mean in space? It's not entirely clear, especially considering that when you leave an orbit as a satellite, when you leave your particular mission orbit, you can't do your mission anymore. It's very likely you can't do your mission. So how do you find an advantage? By maneuvering constantly. So this is me advertising our space paper, our space maneuver warfare paper. We have a debate series where we talked to a military strategist and an astrodynamicist, and they pitted against each other on this topic. But it's something that continually comes up in my work. So go ahead. Sorry, there's a question.
No, nope.
Okay, just making sure. All right, so maneuvering on orbit, the fun stuff. So maneuvers are measured in this thing called delta V. So that's the change in the velocity to reach the target orbit, measured in meters per second. And satellites are launched with a set amount of fuel, and that fuel is budgeted according to the maneuvers that the operator plans to make as part of the satellite's mission. So different types of missions and sizes of spacecraft will carry different fuel capacities. And there are two major types of maneuvers. There's plane changes and there's altitude changes. Plane changes, which is shown in the far left here, are very expensive because plane changes require a lot of fuel. At lower altitudes, so when you're going faster at a lower altitude around the Earth, there's a greater change in velocity that is needed in order to change planes. So the lower the altitude you have, the more delta V it requires to change your plane. So therefore, most of plane changes happen out in geosynchronous orbit rather than in LEO. And to do a plane change, all you need to do is do one burn and burn is like expending the fuel. And you need to do that right at the place where the two planes meet. So your target plane and your current plane. And so that requires maximum waiting for half an orbital period to apply your burn. And when launching from a higher latitude launch site, a plane change may be needed to reach the latitude or reach the inclination in the plane that you're looking for your particular mission. And that's because at the latitude at which a satellite launches is the minimum inclination at which the satellite can enter orbit. And so if you're launching at, say, the North Pole, like you're going to be launching into a polar orbit unless you do a plane change when you enter orbit. So changing altitude in contrast requires two burns at a minimum. So the first burn will put you on what's called a transfer orbit, and it'll intersect with your old orbit. One point will intersect with your old orbit and a new point will intersect with your target orbit. And so then when you reach your target orbit, you can do another burn and get into the orbit that you're intending to be in. And that is shown on the right. But there's another very unintuitive piece to all of this, is that if you are traveling along an orbit, you actually need to speed up to slow down. So I mentioned this earlier, but objects in higher orbits have a lower orbital speed. So you're moving slower when you're higher up compared to when you're closer in towards the Earth. So what would happen if you were an astronaut standing on a spacecraft and you hit a golf ball, either in the direction that you're orbiting or directly in the opposite direction? So of course your feet would need to be strapped in and all that. And the ball would need to be attached to the satellite. So those logistics aside, say you're orbiting clockwise here along this purple orbit. So if you're hitting a ball in the same direction as the orbit, the speed of the ball, the speed is added to, like, the speed of the ball that you hit is going to be added to the direction. So it's going to speed up, but that's going to raise the orbit when you speed up, and that will actually lower the speed of the ball overall. And that's simply because the kinetic energy of the golf ball converts into potential energy because higher orbits have higher potential energy. So what that will look like from your perspective on the satellite, and please forgive my very crude mouse drawing of this, is if you hit a ball in the same direction and you're traveling clockwise around this, it's going to appear to accelerate out in front of you and then loop back behind you as it goes to a higher orbit and slows down. And now the same thing will happen, but in the opposite direction if you hit it the opposite way. So it'll slow down and then it'll speed up because it'll be at a lower altitude. So it's very unintuitive. And overall, the orbits would look like this on the right. And so you have your normal purple orbit, and then if you hit a ball in the same direction, it'll raise altitude. And if you hit a ball in the opposite direction, it'll lower its altitude and speed up. And the fun fact about this is that in 2006, a cosmonaut actually did this and stood on the International Space Station and hit a ball off the International Space Station. But they did the math and they made sure he hit it in a direction that was not going to come back and hit them in the exact same orbit. And Alan Shepard also hit a golf ball on the moon, and to this day keeps it a secret what brand of golf ball he used. So I just think that's really fun. This is a very confusing part of the talk. So thank you for bearing with me through this. All right, so there's also orbital phasing. In the interest of time, I might not get too much into this, but I did lie. I said there were two main things, the plane changes and the altitude changes. There's also phasing changes. So you can move forward along your orbit. So satellite can move to a different spot in its orbit, either ahead or behind through a similar 2-burn sequence as a altitude change. So for forward phasing, the satellite would apply a burn opposite to its orbit direction. So forward phasing would mean it's trying to move ahead in its orbit. So it would apply a burn in the opposite direction, which would cause it to lower its altitude and speed up relative to its initial location. So if it went opposite, it would do the same thing as that red arc in the golf ball did. It would eventually go faster at a lower altitude. And then you could perform another burn and get back onto the same orbit that you started on, but just forward in the orbit. And there are limits to these phasing maneuvers. So if you try to speed up too much that you actually enter the atmosphere, that's a problem. And you also try to slow down too much, you might hit the Van Allen radiation belts, which are naturally forming radiation belts of trapped ions in Earth's magnetosphere. And so those are the kind of the limitations for speeding up and slowing down to phase. But depending on how much delta V you want to use, you can move faster in your phasing or slower. So why would we even want to do all this? Well, there's security purposes for it. All these concepts come together when we're talking about these security purposes. So for inspecting or intercepting another satellite, you need to get close to it, but you don't necessarily need to be in the same orbit. So your orbit just needs to get close to the target, and then eventually you're in the same, you just need to get close to the target to inspect it. And so that's called a flyby or a conjunction, depending on who you're talking to and the intentionality behind the action. Conjunction is usually an accidental coincidence. And then for rendezvous, that's when satellites are not only in the same place at the same time, they're also, like they are during a flyby, they're also matching similar velocities. So this keeps the objects close together for a longer amount of time so that you can complete a mission. So something like docking would need rendezvous and proximity operations. That's what happens when you match velocity in addition to location. And it can be either willing participants or not willing participants. But an example use of rendezvous would be having a bodyguard satellite that's protecting a high value asset in space. And so the steps of a rendezvous include, first, you do your orbital alignment to match your planes. So that's what we talked about earlier, the really expensive maneuver change. Second, you do orbital shaping to match the orbits precisely. So that'll be like matching the altitude, matching the eccentricity, and the other orbital parameters. And then third, you match the orbital phasing to get to the same position with the orbit. And so after the orbit planes and shaping, the phasing maneuver begins. And how this happens is it slowly approaches the target, and from the target's perspective, it'll appear to loop around the orbit. And now this is really unintuitive, so I will send the link out to anyone who wants this, of this man who explains it quite well. But I will show you what this kind of looping motion looks like. So this is your target orbit. And if you change your altitude to go on from this orange orbit to this green orbit here, watch very closely as the green satellite moves around the orange orbit. So you'll see it kind of performs it'll like loop around that spot where it's intersecting with that orbit. So that's the kind of motion that you would expect when you're trying to phase towards a object that you're rendezvousing with. And so that's when this is shown in slide 3 of the rendezvous and proximity operations. That's what that motion is doing when you're phasing in to meet something. And then you perform one final burn to get close to that object. This is kind of a massive oversimplification of rendezvous and proximity operations, but this is like the basic intuition behind it. So I have like 4 more slides. So I want to pause here because this is probably the most complicated part of the top. And if anyone has questions, now's a good time.
You have a question?
Yeah, I had a question. So you're talking about that certain orbits are limited by where the launch point is. So that
yes,
inclinations can only be reached if you have a certain launch point. So
Mhm.
different countries have different places that they can launch things from. So
Yep.
there's certain countries where you'd be like, well, I can launch a satellite and nobody can touch me because I've got this particular latitude here.
Well, you're always able to maneuver. So once you get to that particular, once you launch, it's just it affects what orbit you can launch into, right? So if you're trying to avoid using all of your satellite's fuel to maneuver, you want to launch from somewhere that's actually probably very beneficial to the mission you're trying to do. So that really depends. This is why Australia is such an incredible place to launch, because they are closer to the equator in the sense that that's that minimum latitude. You can go to pretty much any latitude, any inclination from that point if you're launching close to the equator. In addition, you get the extra boost of the Earth's rotation, so you're moving faster already when you're on the equator. And so you have to use less fuel in your launch vehicle. So all that's to say is you can still reach other orbits once you get there, but it's beneficial to saving your satellite's fuel to launch from certain latitudes.
One in the chat, yeah. Can you read that?
Oh, I can get it. So there's a question in the chat. These limitations assume chemical rockets. What do nuclear powered ion thrusters enable?
That is a great question. So that's a big debate, actually. And I'll point you back to the debate paper because I think the astrodynamicist tackles this question quite well as well. So the nuclear propulsion isn't as there's not as much power behind it as the chemical propulsion right now, and I think that's probably changing in the sense that like there's a lot of R&D going on about nuclear propulsion and other alternative fueling for spacecraft. But that's one of the main problems right now is that you can do it, but it would take a lot longer. And so for the security purposes that you're trying to do, that's often the trade-off is the fuel versus time question. So I'm willing to expend a lot more fuel and get there in a quicker amount of time, or it'll just take me a long time to get where I want to go, but I'm going to save my fuel. And so oftentimes the nuclear propulsion, since it just doesn't have the same power, will be in that latter camp. So that's one of the things, but I do think that they're trying to work on that.
In the back?
Yeah. So this synchronizing correction, what are the odds, like if someone was working on something in a spacewalk and they dropped their tool or a nut or bolt, that something would come back and hit the original craft?
That's a good question as well. Yeah, so it's unlikely that it would be back in the exact same spot at the exact same time, but it really depends on the direction that it went off in. But you'd have to have like the exact right impulse for it to be coming back exactly where you would be. So it's highly unlikely, and you have to remember space is really, really big. So the problem that I personally am most concerned about isn't the one-off objects, although those are important to track, especially like dead spacecraft where they're harder to see because they're not emitting any radio frequency noise, things like that. So they're harder to see. But it's things like when two satellites collide and cause a lot of debris. That's a big problem, more than the one-off dropping of a tool.
So you talked about being near another option, whether it's for a flyby or conjunction or shadowing. What kind of distance are we actually talking about here?
So for that's actually a really good question. That kind of leads very well into this next slide here. If you don't mind me jumping to that, just because there's really not a good definition for what is an appropriate keep out zone for a satellite pass. And so there's a lot of conversation about norms in space and how do we make sure that when someone is acting in space, they're acting responsibly. That's a big open question. So something that's been said is 10 kilometers is kind of the no-go zone. But again, that really depends on the mission. That depends on what they're trying to do. It depends on the cultural interpretations of the particular actor involved. So close approach tolerances are judged by all those things. You can also appear to be safely approaching or innocently staying further away from your target by matching planes and performing small burns to engage whenever you want to. So there's a way to like hang back and then slowly approach and perform a burn. And so there's not a good definition for keep out zone, and there's not a good definition for and there's ways to like be more secretive about it. So regarding the distances question, like flybys, it'd be, you know, on the order of like dozens to 100 kilometers, something like that. It again depends on the purpose, but.
Would the final scene in The Martian be even possible?
The final scene of the
Martian. You see The Martian, the rescue scene?
Yes, it's been a while. Remind me what happened.
Well, they had to match the orbit of Matt Damon as he came up, launched from the surface of Mars. They had to slow their ship to get to the right orbital plane distance, and they had to make adjustments in speed. Where he just tore a hole in his glove and he just was zooming around trying to adjust his speed at the end.
Yeah, the lack of control on that would be my concern. But yes, there is a way like to make those fine-tune adjustments. I want to point you guys to a really good example. I can't remember the name of it off the top of my head, but there was a really good example when they tried to do rendezvous and proximity operations for like the first time way back in, I think, the 60s or 70s. And like a pilot, you know, is sitting in and trying to maneuver towards what he sees is the spacecraft, right? And every time he does that, he's like getting further away. And so there's a really good, I'll see if I can find, I'll send some links to Randy after, and he can maybe send them out to folks if that's okay. And it's a good demonstration of like, where you're aiming is not always where you're going. But yes, you can still make some fine-tune adjustments. They're just not as easy as like, look at where you're going and go in that direction, if that makes sense.
Yeah, I suspect in the calculations, they have to have some relativity adjustments since the orbits are different. Or, I mean, they must, don't they?
Like for yes, in a way, that's a really big deal for like signals. So like GPS has to do all of those relativity based adjustments because of the like time delay between sending the signal and receiving the signal. That's all calculated within that. It's, I think, less of a big deal when you're actually maneuvering, just because you're not moving at close to the speed of light at that point. Yeah. Okay, so norms are really important, is the main takeaway from this. And we don't have a good norm for keeping out and keeping away from someone's spacecraft. All right, so a couple more slides, and stop me if I'm spending too much time, but I've got like 3 more to go. Okay, sounds good. Thank you. So kinetic engagements. So there's several broad approaches to like physically engaging with the satellite. So there's, but the most common is anti-satellite weapons. So ground-based anti-satellite weapons are missiles, and they're launched from, well, a point in the ground. They're launched at the right time so that they intersect with a target's orbit at the right time. And so the approach is refined. This is kind of back to your question just now. It's refined by firing thrusters on the warhead to get closer to the object at the right time. But the most part, you're intersecting the orbit. However, there's not a lot of fuel on board a warhead to course correct if the satellite were to try to maneuver out of the way. So once you launch that, you launch it, it's going in a very particular direction, and you can only do fine adjustments. From launch, targets in LEO are about 10 minutes away, and targets in GEO are about 5 hours away. So that's from launch to orbit. Orbital anti-satellite weapons are also possible. And so that's when you station a weapon on orbit, and it's put there in a way that allows you to eventually get closer and destroy a target. And so they can be placed months or even years in advance. And you could take advantage of this kind of secretive maneuvering that I was talking about earlier to avoid detection or seem like you're acting safe when you're not. And besides delivery methods, there's different types of collision. So there's head-on collision. So that would take, you wouldn't have a lot of time to course correct because you're going in the same direction as the satellite. And you also create a lot of debris in that type of collision that's head-on. But also the delivery method is usually limited to being a missile because you'd have to, in order to do that, we'd have to do what we talked about earlier and launch a orbital anti-satellite in retrograde orbit so that it matches with the target satellite's path directly head on. So that's when you do the opposite launch. I don't know about having satellites in orbit still. I do want to look into that. So head on launch is mostly done by missile, or head on collisions are mostly done by missiles. T-bone collisions are when two orbits cross at the same time. So that can be caused by what we, said the flybys and interceptions were like earlier. It doesn't require plane matching, but it allows for easier attack disguise as a result. And it also creates a lot of debris. And the tail-on collisions are interesting because they're not very high velocity, and there's also less debris created. And plane matching, however, is required. So it's that expensive maneuver in order to get there. And so I have to talk a little bit about electronic warfare and directed energy. And so the idea behind this is that non-kinetic attacks can allow for attacks from a distance. And so this can make also non-kinetic attacks harder to attribute because you can't say, oh, well, they launched a missile and now our satellite has been taken out and we can point to the country that did it. This is a little bit harder. You don't know where the signal or came from. So electronic warfare attacks can be administered from the ground, from the air, from other objects in space. They can jam signals, or they can send spoofed data or commands, so like fake data. Now, on the other hand, directed energy attacks, they're highly concentrated electromagnetic spectrum attacks. So they'll usually come in the form of lasers or microwaves, and they can be either reversible, like by just temporarily blinding a satellite, or they can permanently damage the instruments on board. Distance is a primary advantage for these attacks.
We have a question, Katie.
Yeah, go ahead.
Yeah, okay, I was kind of curious if we're gonna talk about the cyber attack stuff here. So I know, obviously, we're sending communication stuff to satellites back to their home. So I'm kind of curious about the infrastructure behind all that stuff, and obviously you can't speak to some of this stuff, you can't. I'm just kind of curious, do satellites have an IP address where I can SSH into it, and what's air gapping essentially the rest of the world from the satellite infrastructure? Because obviously there's multiple components to the satellite. Obviously there's the infrastructure that supports it and communicates back to the ground station, and then there's the operational side of it that does the measurements, takes the pictures, all that other stuff. But the control plane, I'm kind of curious about. Is this off the shelf equipment? Like, if we're talking IP, is this is this all Rocky, something like that? Is this UHF radio, VHF? What's the layer 1, layer 2, layer 3?
I was seeing if I could just quickly, oh my gosh, I have my stack of books, and one of them is cyber persistence theory, because unfortunately I don't know a ton about the cybersecurity side of things. And that is a really, really good question for space, and something that I'm interested also in AI. I think everyone is. And AI is something that can potentially help with the cyber attack side of protecting space assets. So cyber attacks are, I don't know that I can answer that question very well. I just know that they target the data. They're different than other electronic warfare.
So you're thinking that they're more after the data that's being collected as opposed to the control plane that operates the satellite?
Yeah, usually cyber is more about the data or injecting malicious code, something that can lead to loss of information or loss of a vehicle is kind of what we're talking about, is permanently making it so they can't not just communicate, but like that you don't know where it's at other than through just trying to find a piece of debris.
The one thing that pops in my head is I remember one of the Mars rovers got hit by Log4j.
Got hit by what?
Log4j was a vulnerability that hit like a lot of web servers. And just it was all over the cybersecurity news, if you will. Log4j this, that.
Yeah.
And then I found out, one of the Mars rovers got affected by Log4j. And I keep thinking to myself, like, okay, do you bother patching it? Who's going to exploit it?
Yeah, I don't know. I don't know all the specifics on how they actually encrypt. But yeah, that's a really good question. I'll look into that. Yeah, so back to kind of the electronic side. I think, the main takeaway here is that precision is really important when you're you have to figure out how to signal match if you're going to be spoofing or jamming something. So you have to match the right frequency, the right polarization of the signal, and the right signal strength. And if you're going to be spoofing, like faking data, not in the cyber sense, but in the actually like EM spectrum sense, you have to know as much as possible about the signal in order to fake that data. So that's a challenge. And the intensity dissipates with the square of the distance from the source. And so that's a consideration as well for that power, like I was talking about earlier with the broadcasting. And I think that this is the best part, is that you hear about all this in the news. And so it's like things to look out for is just like things you should know. One of the things that interests me most is the idea of high altitude nuclear detonations in space, because they keep me up at night. The most out there, this is one of the most out there kind of examples of space warfare and space attacks. So basically in the 1960s, there were a series of nuclear detonations that took place at high altitudes and even in space. The most famous of which was Starfish Prime, which is shown in here in this image. And it eliminated nearly every single working satellite at the time and prevented the satellites launched in the coming days and weeks from working as well after the detonation. So the Outer Space Treaty prevents the placement of nuclear weapons on orbit. So and any weapons of mass destruction on orbit, but nukes as well. But in spring 2024, so last year, there was a lot of public discourse about the potential that Russia was having a satellite that could be carrying a nuclear weapon on board. It has since lost contact with it. It spun out of control, I believe, in recent months. That was in the news, so that's something. But this was confirmed by the National Security Advisor at the time, Jake Sullivan, and it was also confirmed by the Assistant Secretary of Defense, John Plum, that these were the suspicions that this could be a potentially nuclear-capable satellite. And why this is such a big deal and possible is that satellite data is really helpful for Ukraine right now in fighting Russia. And so Russia has said that they are open to any potential way to mitigate that, especially like when it comes to like Starlink. They said commercial assets could be potentially a target as well, and that would be affected by a nuke in space. So something to watch for. Again, like a lot of this work, there was a lot of work done in 2008 about electromagnetic pulses as a result of these that would affect the ground, but they could definitely affect space as well. And again, I'm going to nerd out very quickly in my dynamic space operations, which is similar to the maneuver stuff I was talking about earlier. This is a term that was coined by Lieutenant General John Shaw in a paper. He was general of the U.S. Space Force, and he used it to describe moving from these traditional predictable orbits to moving towards a more dynamic approach for space. So maneuvering more, switching frequencies, doing things like that to act dynamically and get to these positions of advantage. So since then, you might hear around in the news the term dynamic space operations when you're reading about space. But it hasn't had a clear definition so far. So one of my next goals is writing a paper that defines this and helps us think about what that actually means for the space community. But it would be a paradigm shift. And lastly, I think we've all heard about the return of space-based interceptors in the news. Well, this isn't a new idea. The Strategic Defense Initiative back in the Reagan era during the Cold War sought to eliminate the need for nuclear weapons at all as a strategic deterrent through the use of this program called Brilliant Pebbles, where we'd essentially deploy a bunch of these space-based interceptors and shoot down any ballistic missiles using them. At the time, it was really ambitious and too technologically challenging, but times have changed and there's renewed discussion about having this multi-layered missile defense that includes space-based interceptors in the Golden Dome for America project. And we also have a recent space budget paper that describes just how much money is going to this project. So I can't get into too much of the details here, but I would be remiss in talking about the physics of space warfare without talking about this. And then I'll leave you guys with just my list of recommended reading and and books and things that I find are really interesting. And I have a never-ending list of books myself. So with that, I'll take any final questions and thank you for the extra 5 minutes. And I'm sorry that I went a little over.
Great. Thank you. We'll give Robert a pass. We'll just take a few more questions, John.
So I had a question about the work that you do. I'm John Jackson. I teach here at RCTC at Rochester Community and Technical College, and I teach astronomy. And some of my students, though, most of my students are not science makers, but some of them have expressed interest in policy making jobs and such like that. And you're a scientist who has gone into policy making. You work with policymakers who are now getting into the science?
Yeah, so it's actually I like that question because the debate was, how do I end up doing policy? I knew after my first internship that I really wanted to do policy, but I was approaching it from the science angle. I was always told, stay technical until you know that you want to stay in policy for a while. So there are certainly a lot of policy people who are very, very knowledgeable about the science side. But the key is building that science knowledge enough to be able to talk to the engineers who do it. So I definitely know of a ton of people who have started in science and moved into policy. And now at this point, I know a lot of policy people who don't necessarily, get to the point where they're like publishing science research, but they can understand it and talk to the engineers who do it, if that makes sense. So there's certainly a lot of jobs that support this kind of work. And there's more than you would think about. So like there's the communication side, there's the strategic planning side, there's the actual like operator side. There's a lot of people who are in the Space Force who don't necessarily have technical degrees, but are space operators. So yeah, there's a lot of options. And if you have students who are particularly interested, and especially from a science background going into policy, like let me know, and I'm happy to talk to people.
Yeah. There's one leftover question from the chat from Steve. We already talked about energy beam attacks, but garbage cleanup probably has to use some of the same orbital science mechanics.
It absolutely does. Yep. It's very similar. All the rendezvous proximity operations things. Yeah, that's when that comes into play. But like I said, think about the dual use nature of it. So if you have something that can grapple a piece of trash in space, you can also have something that can take out an active satellite. And so that does cause concern for some people. And should be part of the consideration. Yeah.
Two more questions, then we'll respect your time here and wrap up. John, you had
John, again. In addition to teaching astronomy, I'm also the advisor to the Tabletop Gaming Club.
Mm-hmm. And are you really?
And so I'm wondering, the tabletop games that you guys play, are they anything similar to the games that my students might play, or not?
So I'm assuming are you talking like Warhammer, that kind of stuff? Like
yeah, that kind of stuff.
Okay.
There's a lot more to understand, but there's a lot of Star Wars type games and stuff like that. I'm wondering, does it look like that when you do a gaming exercise?
So it depends. Wargaming is something that I'm super nerdy about as well. Because wargame can mean an actual physical like board game version. where you're actually moving around pieces. There's a whole field dedicated to wargaming. And if any of your students have like an interest in going into a career in that, I have lots of resources for them as well. I'm just all the follow-up emails. Just send me any questions you have, and I'm happy to answer. But most of the ones that I do are like we call them tabletop exercises in the sense where it'll be like a scenario, and then you're working with a team to try to figure out like work backwards. You're given a scenario for 2045, and you have to work out, how did we get here? What decisions did we make? How do we prevent getting here from the future if it's a future we don't like? So it's putting the right people in the right room on the right team. So it's both human knowledge as well as like creating a scenario that's actually pretty realistic. But yeah, so it's a range. The war game I built for school is a physical board game, and the stuff I do at work is more of the scenarios. Yeah.
Jay.
Back in the Reagan era, there was a lot of talk about using lasers as a defense weapon. What's the status of that now? Last week we heard that when China had their big parade and got together with Russia, they had some laser equipment. What's the status of that now? Are we developing lasers for defense in space?
Yep. Yes, we are. That's the whole idea of, and it's confusing because it's electromagnetic, or it's the electronic warfare versus directed energy. That's the directed energy side, is the laser side. And yes, they are absolutely developing that. And that's where I look at the Secure World Foundation's counterspace report that really gets into who is doing what, who has what capability in the directed energy. And there's more and more countries who are interested in potentially using those and developing those weapons. So certainly an interesting time to be in space.
Is that a practical way of destroying things from a long distance?
Yeah, it is, because you can still permanently destroy something by permanently blinding it and damaging its sensors using directed energy. Yeah. Yeah, agree. Whoever put Steve, yes. Pennies per shot versus 1 million per missile. Yeah, that's a really good reason.
One last question.
So I kind of imagine as practicing warfare, they could be playing laser tag from satellite to satellite.
Yes, I mean, I think so. That's part of like when you're maneuvering closer to a satellite, you have to do a couple of those fine tuning burns to like get your actual weapon. Like if for the tail on collision that I was talking about, that's when you'd actually have to use a weapon. You could, in theory, use a laser as well as just like a kinetic actual weapon. But you have to be very precise about where you're going, and space is really big. And so there's still that proximity issue of like, how do you have to know where you're pointing. And so as long as you can do that, then there's a risk. Yeah.
Yeah, it doesn't need to have like kinetic calculations involved. Like there would be no splat ball in space. There would just be laser tag bots.
I hope we don't get to that point, but yes.
Well, thanks again. I think we could probably go another half hour.
Yeah,
To be honest with you, but we'll connect again, and we'll connect with some of the links you wanted to share with us too,
Okay.
and some other.
I'll just send you a whole bunch of stuff. So thank you.
All right, one more round of applause, and we'll let you go.
Thank you, guys.
All right, you have a good evening. Thanks for all your time and information.
Thanks, of course. Bye, guys.
Bye. Thank you.
All right, we'll shut down for just a few minutes. Let's take a break. Come right back into the meeting. Yeah, that's good stuff.
Thanks, Randy. That was really
Yeah,
good.
I think she